Hello students, I am Dr. Tanmoy Biswas. I welcome you all in my channel Chemistry, the Mystery of Molecules. Today's topic of discussion is cryptochirality. Chirality word, you have heard about it. But what is cryptochirality? We shall discuss. And we shall know one answer. Can chiral molecule have zero specific rotation? Because specific rotation is a characteristic of a chiral molecule. So is it possible? How much? What is its implication? And how this concept could be utilized in synthetic chemistry? We shall learn everything in this video. But before going to details, one question or MCQ. I request you student, please pause the video, try by yourself, and whatever answer you get, please write in the comment box along with few words as explanation. I believe you have tried. I shall give the answer of this question at the end of this video. So let's start. So question, the obvious question, what is chirality and optical rotation? In chemistry, a molecule or ion will be called as chiral if it cannot be superimposed on its mirror image. That's a mirror non-superimposable mirror image relationship is the basis of chirality. And it could not be achieved by either rotation or translation or some conformational changes. So you cannot mix. Actually, they are two different molecules. And this geometric property is called as chirality. Means orientation of bonds in different direction. Mainly we'll say three-dimensional rotation, but that's a very crude definition. Now, next point, what is optical rotation? Chiral molecule actually interacts with plane of polarized light and can rotate the plane, and this means either it could be right side or this side, means like clockwise, or you can say anti-clockwise, and this phenomena is called as optical rotation. So presence of a chiral compound you can detect by plane polarized light, and optical rotation is dependent on the property of that molecule itself. Now, so you can see example. So here if you look at this central carbon atom, it is attached to one type of group, two type of group, and here both are same. So that's why its mirror image, this both are superimposable to each other. You can rotate it and fit it, it will be. Now, so or you can think that sir, you can rotate in this direction and you set it, it will be fitted. Now fine. Next, that's why this molecule is called as achiral, and its mirror images are superimposable, could be fitted just point to point. Now if you take another molecule where four substituents are different, ethyl, methyl, hydroxyl and hydrogen, so this is not superimposable with respect to its mirror image, this one. That's why this molecule is called as chiral molecule, and this mirror image are non-superimposable to each other. By the way, this molecule is nothing but 2-butanol. I am not going whether it's R or S, that's a different, but it's an isomer of one isomer of 2-butanol. This is the another one. 2-butanol is actually this chiral molecule. Now here, if you look at the example also possible, other many example where carbon is attached to four different substituents. So in a very crude way I can say, by the way, this is means front top side, this is bottom side, this is plane C, and this is D. So this is a small c. Okay, by the way, let's take something else, E. Let's take this is E. So A, B, D, E, four different substituents are attached with this tetrahedral carbon. Since they are different, so that's why it will be called as chiral carbon. Now what is cryptochirality? Cryptochirality is a special case of chirality where the molecule is chiral, means it is attached to four different groups, but its specific rotation is non-measurable. Actually, if I say it is so less, it's actually very less, means when plane polarized pass through the solution of this molecule, then actually the specific rotation is very less. So that's why it could be very difficult to detect. And who shows this property? Chiral saturated hydrocarbon or saturated quaternary hydrocarbon. Saturated means no double bond or pi bond there. So these class of compound can form such kind of actually shows such kind of cryptochirality behavior, and because of that it is very difficult to distinguish them because the specific rotation of these chiral compounds are very less. So you can see one example. Look at this carbon center is actually chiral. So one side is actually C4, I mean carbon 1 carbon 2 carbon 3 4, in this case 3. So it's a C3 attached, C4 attached, C2 attached and C6 attached. So this is the S isomer and its mirror image. Its mirror image, these R1 and it looks this. So actually this is, both are chiral compound and the relationship between this structure and this structure is the enantiomer. So they show cryptochirality. Now actually a question you may think that, is chirality really exist on some asymmetric saturated quaternary hydrocarbon? Actually, or you can see, sir, the optical rotation is very less. So is it almost a racemic mixture or pure chiral compound? That's an important question. So since I am talking the specific rotation value is very less, so from optical rotation measurement it is very difficult to conclude. Then question, how can we do utilization of its application? So based on that we can detect it. So for that purpose the concept of chiral environment versus asymmetric synthesis is very helpful. What means? It means enantiomer behave similarly in achiral environment, but their behavior changes, or they behave differently in chiral environment. And this concept is utilized for asymmetric synthesis. Means during the preparation of an optically active compound, chiral environment provides the preference for one particular enantiomer over the other one. And that's why enantiomeric excess is obtained, or you can say that one particular enantiomer is obtained preferentially or more amount or sometime completely. And this is the student one of the basic concept of asymmetric synthesis or chiral synthesis. So do some chemical reaction in chiral environment to obtain chiral molecule. That is the basis of this concept. Now based on this concept you can say whether this molecule whatever is produced here, you produce enantiomeric mixture or particular isomer. For that purpose you can see two types of reactions are designed. So here it is actually this dinitrogen containing aromatic ring attached to this aldehyde, and these aldehyde student is reduced using diisopropyl zinc 2.2 equivalent. Actually one equivalent of this isopropyl group is transferred. Now we know that this part is actually the nucleophile and this carbon is the electrophilic center. But how chirality is introduced? By these enantiomer or these hydrocarbons. So this reaction is carried out of inside these molecules environment, this chiral molecule. Now we will say, sir, it's a pure chiral molecule you're using. Yes. And what it result? Look at 89 to 93% yield of this reaction, where 93 to 97% enantiomeric excess. Wow. In this case, this isomer is obtained, obviously S isomer. Similarly, if you take the another enantiomer of these isomer, means S version. So in that case, what is obtained? R isomer, this alcohol, where 91% yield and 94 to 95% enantiomeric excess. Now question, why this change in asymmetry or enantiomeric excess? Obviously because of the chiral environment. And who is providing chiral environment? Either these hydrocarbon and here these hydrocarbon. Now from this discussion it is proved that whatever molecules are there who is showing very less optical rotation, they are not racemic mixture, they are particular chiral molecule with a very low specific rotation. So this example actually proves about the optical, it's actually the purity of this molecule in actually obviously say one enantiomer. So enantiomeric purity of this molecule versus chiral, this its application like chiral synthesis. Now from here I guess you feel interest, sir. Wow, great science. So how can I prepare this molecule? Student, it is little different time. So let's go about its synthesis. So we are going to synthesize these two molecules, this one and this one. How? By enantioselective method. Why enantioselective? Because if you do a common synthesis, simple synthesis, and if you prepare this two, you think that okay, enantiomeric excess I shall prepare, means from parent achiral molecule, if you plan to synthesize one of the enantiomer, then you cannot detect that what is the percentage, what is the ratio, because optical rotation which we used for this detection of molecule, that's very less. So using that tool you cannot say you got chiral or racemic. So for that purpose enantioselective method is needed, which will confirm us whatever reaction we want to do, we got it. So for that purpose this synthesis method is utilized. So this is thiophene, Actually it's a 6 pi electron containing aromatic system, more active because 6 pi electrons are distributed on 5 atoms, 4 carbon, 1 sulfur. So this thiophene is actually pi excess nucleus and it is reactive for aromatic electrophilic substitution. And what we are reacting? We are reacting a C2 C3 ketone in presence of sulfuric acid. Now what sulfuric acid does? Sulfuric acid protonates this ketone and makes this carbon actually a better electrophile, such that aromatic electrophilic substitution can occur, and in the first step you can expect this compound. So here OH, it is ET and it is PR, propyl and ethyl. Fine. Now in the next stage, what you can expect? This sulfuric acid is there and this alcohol is student, it's a tertiary alcohol. So tertiary alcohol will go further protonation and these OH2 plus will leave and ultimately produce a carbocation. So in the next stage, this carbocation will act as the electrophile and another molecule of thiophene will act as nucleophile. So in another molecule of thiophene, aromatic electrophilic substitution will happen and it will produce this dithiophene containing, one side is C3, another side is C2. I will call this name because it is easier. Now still this molecule is not chiral, it is achiral. Why it is achiral? Because two thiophenes, same molecules are there. So I need to make at least one thiophene different such that I can make a chiral molecule. For that purpose you can take acetic anhydride and obviously perchloric acid. Now perchloric acid, I know it's a very strong, so what it does, it first this perchloric acid protonates acetic anhydride and makes the acetic anhydride, protonated acetic anhydride, which is actually a better electrophile. Fine. And here any one of this thiophene will attack. So here left side is attacked and produces this acylated product. Acylation means COCH3. This is a significantly polar molecule, so that is produced. Now this molecule is, student, actually significantly polar, so it could be separated using chiral HPLC. So this HPLC resolution technique is utilized to separate the enantiomeric mixture. See, look at here, this carbon is chiral carbon, but till now I have here racemic mixture. So that's why it is separated by HPLC. So from this HPLC separation, what is obtained? One is this R isomer, this one 99.5%, greater than 99.5% enantiomeric excess. So you can say it's completely this R isomer. Another is its opposite S isomer, where you can see it is also greater than 99.5% in enantiomeric excess. So pure enantiomers are separated, fine, but still not our hydrocarbon obtained. So in order to get that, what is done? First look at, there was a carbonyl group. So this carbonyl is reduced by this Wolff-Krishna's reaction. So by the way, I've already discussed a dedicated lecture. I request you, student, please check the I button and the description box because lots of related lectures link are given there. So after Wolff-Krishna's reduction, this acetyl group CH3CO is reduced into ethyl. Now look at, this is one type, this is another type, this is C2, this is C3. So 4 different parts of carbon chain are attacked, but still it is not the product because it's a purely hydrocarbon, not any aromatic ring was there in the product. So that's why these sulfur removed, 2 sulfurs are removed and these 2 double bonds are hydrogenated using this combination. Actually, if you say Rani nickel means nickel adsorb hydrogen, highly porous nickel catalyst adsorb hydrogen. So these hydrogen is actually responsible for the reduction or dearomatization process. So saturation will obtain and this nickel will combine with this sulfur and produce nickel sulfates. In this way catalyst will be destroyed. And see, in this thiophene part, whatever I am talking, so this thiophene part, it has 4 carbon. So 1, 2, 3 and 4. So this side will be reduced into C4. Why normal? Because it's a chain, so you can see it's a chain, so C4 will be obtained from here. Similarly 1, 2, 3, 4 and ethyl 2 carbon, so 5, 6. So in this way 6 part. So in this way what we got? Pure enantiomeric compound. By the way, this chiral center will not be affected during this reaction because this reagent is selective. Just sometime before I told selective method for or enantioselective synthesis. So this is a selective reaction, that's why chiral center will not be affected. Just this aromatic ring will be hydrogenated, reduced and sulfur will be removed. So same thing is applied for the S isomer, so you get this S hydrocarbon. By the way, they are already separated. See, in this step it is separated. So next step I am taking pure enantiomer and doing this reaction. So do not get confused, and this is the reference. Now, so actually this is the actual reference paper. So if you want, you can visit. So here you can see the application of this molecule. So in conclusion, what you have learned, that carbon atom attached with 4 different substituent results in chirality in the molecule, which is measured by specific rotation. It's a common technique. But if the asymmetric carbon atom is attached to 4 different alkyl group, then it results chirality, but the specific rotation is very less, or you can say almost undetectable. So how you can prove its presence? The presence could be detected or proven by asymmetric reaction or asymmetric synthesis reaction, where this molecule is responsible, means pure molecule is responsible to provide chirality. So I have explained the example. And finally, remember this statement: enantiomers show similar chemical and physical properties in achiral environment, but their properties changes in chiral environment. Okay. Now let's go to our MCQ. So which kind of radiation most suitable for exciting saturated hydrocarbons? Alkane. So in alkane there are 2 types of bonds, CH and CC. By the way, both are sigma bond, and if you look at the molecular orbital diagram, sigma is maximum stable and sigma star, it is in top, it is maximum unstable. So you can conclude, sir, this energy gap delta E is maximum for this saturated analog or alkanes. Now question, since this gap is higher, so you need to select one particular radiation whose energy is maximum. Now among these 4 options, which have higher in energy? Now if you look at radio frequency, it is minimum energy. Infrared, okay, it is beyond visible, okay, then I can say less. Visible rays, it's a moderate energy. And who is, that is UV ray. So this option A is the answer. By the way, one information I want to give, if you arrange them in an order of energy, then UV rays, A option is more energy than visible, then visible is more energy than IR, option C, or another is D, radio frequency. So these information, student, remember, it will help you. So this is the end of the discussion. I believe this video may be useful. Thanks for watching. If you enjoy my content, please help this channel to grow, or you may visit 2 of my another channel.